So I want to talk about three equations, which, with regard to converting annual percentage rate to effective annual rate, which in a sense are really one equation. They just are used in different ways. And let me just start up here. And there's an equation called the equivalent end period discount rate, abbreviated discount, okay? And it's equal to 1 plus r, the interest rate, raised to the n power minus 1. Now, n could be less than or greater than 1 in this case, okay? So I call this equation A. Now, this is the most general equation, and the other two we see are all going to be derived off of here, okay? This is the most general equation. All right, and then there's an equation where you may have a return, and what you may want to do is you may want to find out what is the, like, say you have a return for like a month, and you want to know, well, what would the equivalent or annualized performance be over 1 year? I want to, equate it to a 1 year return so I can compare it to everybody else, right? Now, if you look carefully at this equation here, which I call B and A, you can see that they are almost exactly the same. Now, R in this case is simply the final value over the initial value, right? So you can get that R just by getting this. And you see I call that equal R, okay? Now, this one says to the n, and this one says to the 1 over n. And this is because what you're basically doing is you're taking a return that's less than a year, right? And you want to convert that in, or you have a return that's several years, actually, right? Several years. And you want to convert that to an annual return. So let's say you have something for 5 or 6 years. You would put a 5 or a 6 here and take the 1 over that. And that would give you your annualized performance. But the important thing here is you have to know how long you've held it in this case, right? In this case here, n could be greater than or less than 1, so you can get a discount rate for a period less than a year or more than a year, right? So, but this basically sends it now down to 1 year. But again, they're almost exactly the same. It all depends on how you define the 1 over n term. Okay, so n is in years here. Now, the term 1 over n can also be expressed, like, if you don't want something in years and you want something more, smaller periods, like days, right? The term 1 over n can also be expressed in days, and you would just replace 1 over n with 365 divided by n, where n is the number of days, okay? So let's say you had something for 2 years, which is 730 days. You'd put that here, right? And basically, you'd still end up with the same equation, right? You'd have 365 over 730, and you'd have 1 over 2, right? And that would give you your annualized performance, but you can really get it down to, days in that case. So as I said here, equations A and B are actually quite similar, with A being the more general, right? The n and 1 over n are actually the same depending on how you define the time period. B is also defined as the annualized holding period return, right? You'll see that in a lot of books, right? Okay. So often you will see another equation, which I'm going to call C, that converts a non-compounded APR to an effective annual rate, and I call that EAR, like the word ear, effective annual rate. And that's this equation here. Now, what you've got to do is you got to take your annual percentage rate, which is not an effective rate. Now, you know that it's a year, and you divide it by the number of compounding periods within the year, and then raise this to the nth power, okay? So this is a little different than this, but in reality, this here could be APR over N2. Again, so there's a lot of similarities between equation A, B, and C here. okay? And you can see there's the N again. So R could be APR over N. So once again, this is very similar to equation A above. Typically, N in this case is greater than 1 and depends on the number of compounding periods. Okay. All right, so just to show you an example here, you have a monthly payment of $4,000. Let's say you're paying a loan and the payment is $4,000 a month, right? Now, this is important. You see, I say monthly here, right? And you're told the APR, now the bank is charging you, the APR is 5%, okay? Compounded semi-annually, right? So whatever you owe, they're going to compound it semi-annually. And what you want to find out is, what you're looking to find out is, you want to know what the present value is of all the 48 payments you're going to make over time. I kind of didn't say 48 payments here, but there's 48 payments of $4,000 a month at 5%. So the APR is 5% compounded semi-annually. So now the 6-month rate, right, divide that by 2 6-month periods, is 2.5%. However, we must convert this now to a monthly rate since payments are being made monthly. So using equation basically A, we get here 1.025 to the 1 over 6 months, okay? Because this is compound, this is a 6-month rate, and we got to get it to a 1-month rate. So you see I put a 6 here. And it comes out to 0.4124% a month, okay? So we can now use the Excel function built into Microsoft Excel. I don't know if you're familiar with it. It's called PV for present value, and we can find out what the effectively how much we're paying, the present value of these 48 $4,000 a month payments, right? So everything is in months, right? So we can pop numbers now into Microsoft Excel. And we can come up with that. So in Microsoft Excel, I put N is 48 months, right? The rate of is 0.4124%. Now the payment is $4,000 a month, but I make that negative because that's coming out of your pocket. Excel always wants to see money coming out of your pocket as negative. And when I pop it in, Excel just pops the number right out, and it says, well, the present value of 48 payments at 0.4124% a month, compounded every 6 months, okay, for 4,000 is $173,867. Now, the important thing about this is, if someone basically said you can pay $150,000 up front or pay us in payments, you can clearly see that the payments are going to be higher. However, what they're not saying is those that $150,000 you can invest, right, and maybe get a better rate. Okay. So anyway, this is how these three equations are tied together, and they're really one equation, but used in a couple different ways. So I hope I was clear on that, and I'll be putting more stuff on this on here. So I want to just show you how the present value function in Excel is used here. So if you see, I can go up here, right up here, f of x. And right here, one of the choices, there's a lot of functions in here, by the way, and a lot of them are in finance. So you can pick different, see how there's different, like financial here? Many different functions. And you can have a ball with them. So in my particular case, here's our case, is PV, right? So I say, okay. Now, what I got to do is put the information we had in here. Okay. So here's the rate, right? We calculated the monthly rate, 0.4124 over 48 periods. Okay. And here is the payment, which I should have made negative. Hold on. Negative. So you can clearly see the present value came out just as we calculated, $173,867. Okay, so that's all there is to that. And if you just say okay, it gives it to you right there. Okay, so I just wanted to make sure everyone was aware of that. Very good. Thank you.